Now in the real world, it's not that common that all the forces are at right angles to each other. So here's a example taken from a past paper, a couple of ropes applying a force onto a package here. And you see we don't have a nice right angle triangle. You could solve this using scale drawings, but what we want to introduce is an idea called resolution of forces, or finding the components of forces. So that kind of sets a context, but if we look now how we're actually going to do that. So we're going to just look one force at a time to start with. So imagine you've got a force of 100 newtons and it's acting at 30 degrees. And we're saying, what is the components of this force? So let's assume this is a vertical horizontal sort of situation, and that dotted line represents the horizontal. Basically what we want to say is how much of that force is acting horizontally and how much is acting vertically, and they're called the horizontal and vertical components. Now you met this concept a bit in projectiles last year, where we split the motion up into horizontal and vertical components. So we're returning to it again with forces, and we'll return again to projectiles in the next unit. So basically what we're saying is how much force acts in that direction and how much force acts in that direction. And what I'm trying to do here is to kind of line them up so that that one ends underneath there and that one lines up there. That's what these two components are. And what we're doing is basically the opposite of what we've just done, where we found the resultant. This is quite a common thing in maths and physics. You learn how to put things together, you learn how to take them apart. So what we're doing here are finding the two vectors, these solid blue arrows that I've drawn here, which would make up a resultant of 100 newtons at 30 degrees. And so we are still just applying Pythagoras, but basically the opposite way around this time. And I've drawn them in just to show you the direction they're acting, but if we were drawing them as a proper resultant triangle, then this one here would have to be over there, or I could take the bottom one and move it up the top. So this is the horizontal component, and this is the vertical component. And we can just use simple Pythagoras and trig, and we'll base it on sort of the fact that we know this was 100 newtons, that black right in there means that the horizontal was 100 newtons to start with. So what we can say here is, if we call that angle x, then we can say cos of 30 is adjacent over hypotenuse. And can you see that the horizontal component here is adjacent to that 30? So cos of 30 equals horizontal component divided by 100. And rearranging that, then we get that the horizontal component multiply both sides by 100 is 100 cos 30. Okay, and then you stick that into your calculator. It's 86.6 newtons, and by similar argument, if you take the sine component, it's opposite over hypotenuse. Now the sine component here is opposite the angle, it's the vertical component. So the vertical component is 100 sine 30. Which is 50 newtons. So now we've worked out how much of that force acts horizontally, how much of it acts vertically. And if you look at these values, you can see 30 degrees, you're below 45, so basically the horizontal is bigger. It's a good wee check to do at the end if you've got these the right way around. So as this angle gets smaller and it gets closer and closer to horizontal, then the horizontal component is going to get bigger, the vertical component is going to get smaller. And obviously the opposite, if you go the other way, if you increase the angle, go closer to vertical, then the vertical component will get bigger and the horizontal component will get smaller, just following what happens to cos and sine as you go between 0 and 90. And that's what we call finding components or resolution of forces. Now if we return to the example we showed you at the start and try and apply that logic, what we have here is the idea, this is a past paper question, it would be worth 4 marks, so there's quite a bit of work involved, that you've got tension in each of these ropes. Now we can actually simplify things a wee bit by using the symmetry of the situation. I've not drawn that terribly well, those arrows should both be the same length. But what we know is that the weight is pulling down, and then we're going to have to balance that. So we do a quick calculation of the weight. It's 33.32 newtons. And then because of the symmetry of the situation, basically what we're saying is that each of these ropes is going to have to provide half of that. So one rope is going to have to somehow balance the half of that 33.32 newtons. I'm keeping quite a lot of significant figures in the middle of my calculations, remember. We can round off at the end. 16.66 newtons. But weight, remember, is a vertical force. Right, so this is a wee bit harder than the example we've just done, because in that we were given the hypotenuse. But in this one, what we're doing is if we pick one of these ropes, it doesn't matter which, what we're saying is it's got to supply 16.66 newtons vertically upwards to balance the weight, and the other one does that as well. But it's actually acting at an angle of 35 degrees. So how much is the tension, which is the hypotenuse in this case? If you're wondering about that component there, well, the one on the right that I've drawn here will be balanced by the one on the left, pulling with an equal force to the left. So even if we worked out that component there, it would cancel out and wouldn't contribute to the overall force. So using the theory that we've just looked at, we can see that the 16.66 here is adjacent to the angle that we're given. So we're going to use cos x equals adjacent over hypotenuse, which in this case then is cos 35, and the adjacent we know is 16.66 newtons, and the hypotenuse is the tension that we're trying to work out. Now we can rearrange to get that tension. Like I say, it's a wee bit different from the other ones. We were working out the adjacent or the hypotenuse, the adjacent or the opposite. Here we are actually working out the hypotenuse, so the angle ends up on the bottom. But we do the calculation. Calculator says 20.338. We could give that to 3 significant figures, but the data in the question is all to 2 significant figures, so it is actually slightly more correct. The 3 would be acceptable, but the correct answer there would be 20 newtons. Okay, that's showing you a fairly difficult worked example based on this resolution of forces.